All right, so for the next section, we are going to use the 6.4 notes, and they look like this. It says dividing radicals on them, so dividing radicals and then rationalizing the denominator, and they should be 2 pages because it should also say binomial denominators. So we're going to work through these 3 sections here. So in the last sections, we were learning to combine with addition and subtraction and multiplication. And you know that since we are working with PEMDAS, we have to know all of the operations. We've got to be able to get that x out and simplified no matter what way he is there, right? So the very first part we're going to learn is the dividing radicals. It's called the quotient property. It works exactly the same as the multiplication rule that we learned in the last one, which would make sense since division is just the pair of multiplication, so all the rules need to be the same on it. And so I like to look back at something that's very familiar to us, and then we can step into a little bit harder ones for it. So initially, if we had 6xy to the 1/2 divided by 2x to the 1/3 z to the -5th. Okay, so this looks super complicated. Let's back up even further and say if I just had 6xy over 2xz, how would we simplify that? Well, we learned that when we divide exponents, we subtract them, right? We subtract their numbers. We also know that when we're just looking at it, I've got 6 divided by 2 gives me 3. I have an x on the top, an x on the bottom. Those cancel out, and I would be left with 3y over z in that case. Technically, what we did in this case is we said this x has an exponent of 1, the x on the bottom has an exponent of 1, and anything that is divided, we subtract the exponent. So if we have x cubed over x, we learned that that's really x to the 1, and we subtract these exponents. 3 minus 1 leaves us with x squared. So that's our exponent rules. So we're going to use the same rules that we knew before, and we're going to combine them and use them when it looks a little bit different for us, right? So in this case, our constant terms are still 6 divided by 2, which still gives us 3. That's the same. Our x values here, we've got x with an exponent of 1 and x with an exponent of 1/3. We know that's the cube root of 3. The cube root of x there with an index of 3, but we can't divide that well. However, when we're in exponent rules, we can, because my exponent rules just say that when my bases match, I subtract my exponents. So I made my base match, and I just subtracted my exponents. It just happens to be that they're fractions now, which means we've got to remember how to subtract fractions. Okay, my y doesn't have anyone that needs to be paired up with, so he stays down here. And the z, we don't like to have anyone on the bottom, so we're going to move him to the top. Okay, well, specifically because he's negative. And so when we change sides, we change signs. So now that he's up top, he's a positive 5 there. So the only one that we really need to work with is this x, and I've got 1 minus 1/3. So I could say 3/3 minus 1/3 gives me 2/3. So we're able to simplify exponents when they are in exponent form. It's radicals when they're divided. Okay, so there's another way that we can do it if they were written in our radical form. We know that we can simplify them separately, like we can have one on top and one on the bottom, where our radical sign is separate for each of them, or we could put them under one radical sign and have it all underneath here together, all by itself. Well, why would we need to do that? Because sometimes it's easier one way or the other. We're just trying to figure out the best tools that we can use. When I have the fourth root of 162 divided by the fourth root of 2, right here on the bottom, I have something that does not work. I cannot simplify that. However, when I combine them together and I go ahead and do 162 divided by 2 first, I get 81. And 81 is 3 to the fourth. So now I have the fourth root of 3 to the fourth. I need 4. I have 4. These match. My answer is simply 3. So again, we can see that sometimes it's easier if it's on the outside. Sometimes it's easier if it's on the inside. All right? So when we go to divide radicals, again, the most important thing is that the index must match. So that's the very first thing that we're looking for. If the index does not match, we cannot move forward. Once we know that the index matches, we're going to look at our numbers and we're going to decide, can I simplify them as is, or is it easier to combine them? Okay, so let's look at number 1. Here, I have square roots, and right away, the square root of 5 on the bottom cannot be simplified. I can't pull it out. However, if I combine this and I do 12 divided by 2, and I put this whole thing, because I have matching indices of 2, and I have 160 divided by 5. 160 divided by 5 here is, sorry, my brain is so tired tonight. So I'm going 5 into 16 gives me 210. I have a 6 left over. Sorry, I needed a 3 there. 15, so 32. Okay. So now, instead of having 160 over 5, I have the square root of 32. So we can do our coefficients. 12 divided by 2 gives us 6. The square root of 32. Now I need to look and see if I can simplify that guy anymore. So 32 is 8 times 4. 8 is 2 times 2 times 2. 4 is 2 times 2. I need groups of 2. So I have a group of 2, a group of 2. They're both going to pull out. So now I have 6 times 2 times 2. And I've got this one guy that gets left underneath. So 6 times 4 gives me 24. Square roots of 2. So we were able to simplify him from what initially looked like something super complicated and make it a little bit easier for us. Okay, so let's look at this one here. Now, we've got square roots, and I've got numbers that are more than square roots, so I could go ahead and pull them out, but I'm going to combine them first. So since I've got 2 square roots, I'm going to go ahead and put it all under 1 and say x cubed y to the 9th, x squared y to the 5th. And we're going to simplify inside the radical first. Matching bases mean that I subtract my exponents. So I'm left with just an x. 3 minus 2 gives me 1. For my y, I have 9 minus 5 gives me 4. So if I have 4 y's, I have 2 sets. So I'm going to end up with y squared, and my x guy stays underneath. Okay. So dividing, let's look at number 6. We'll look at the cube root here. I've got cube root of 40 over 27. Can we simplify 40 and 27? Well, 40 is 8 times 5, and 27 is 3 times 9. These don't have anything in common, so as is, inside, I can't simplify it any further than 40 over 27. So for this case, if I do the cube root of 40 and I do the cube root of 27, I know right away the cube root of 27 is 3. That was one of our cube roots that we memorized. Now, On top, I've got 40, which I know is 8 times 5, and 8 is my cube root of 3. Sorry, my cube root of 2. I've got 2 3's. So I'm going to pull him out and have 2 cube roots of 5 left over. So a couple of different ways that we can solve that, but with dividing radicals, we are just looking for the easiest way to simplify it. Okay? Now, what we could do sometimes is if we don't like the way that our number is written in a radical, we could rewrite it with a fractional exponent here. Okay, so sometimes, like if you're looking at the ACT, you might be given this with a fractional exponent. So knowing that we have a division, the division rule is that the index has to match. So in either way, we're looking at, I've got an index that matches here, an index that matches there. So we could say, yes, I could try to simplify those. Okay. Now, what is our problem when we have something like this? Okay. Well, the problem is that it doesn't matter which way we have this written. We end up with a radical on the bottom. Okay. And in mathematics, radicals cannot stay on the bottom. So we're going to have to do something called rationalizing the denominator in order to move that radical out of the bottom. Okay? Now, rationalized is a big word. It just means it's not a radical. Right? Okay? And we also see that word ratio in there, meaning that there is a fraction there in the bottom, which we can see that we can write it in a fraction, okay? So this uses a little bit of logic, a little bit of brain. There's not a set rule on it. We just have to figure out what we need each time so that the radical doesn't exist anymore, okay? So for this particular problem, our index is 5. It means that we need 5 of something. So I'm going to write out what we have. And on the bottom, I have a 4. Okay, so I really have 5 times, the fifth root of 2 times 2. Well, I need 5 of them, and I only have 2 of them. So I need to add 3 more 2's for me to have 5 and need 5 and to make those go away. Well, what is our rule in math? I have to have the same index when I'm multiplying. So I'm automatically going to make it a fifth root because I get to choose. I'm making a fifth root and I'm choosing to add 3 2's. Now, math rule number 1, this has to be the number 1, right? So when I multiply by something, I have to actually multiply by the number 1 so that I'm technically not changing it. That means if I multiply by the fifth root of 8 on the bottom, I have to also multiply by the fifth root of 8 on the top. Okay? So this is our number 1, same thing on the top, same thing on the bottom. Now, when I multiply across, my index stays. I've got the fifth root, and now I have 1, 2, 3, 4, 5 2's. 2 to the fifth. I have 5. I need 5. Those go away, and I'm simply left with a 2. So now I have no radical sign on the bottom. So what is the top now? Well, my indexes were both 5's, so it stays an index of 5. I'm going to combine what I had underneath. So I've got 3 times 8 here, which gives me 24. I can't simplify anything out of that because when I combined them, it didn't add anything to it. So we just leave it as the fifth root of 24 over 2. And this is an acceptable answer. It is fine to have the radical in the numerator as long as we have just an integer in our denominator. Right? So let's look at this a slightly different way that we could look at it. If we left it all as one radical, so in this case, we started here and then we separated them out. If I left it all as one radical, where I have 3 over 4, I know that my 4 is 2 times 2, and I need 5 of them. So I need 3 more 2's, which gives me 8. So again, we're multiplying by this number 1 of 8 over 8, so that now we've got 24 on the top and 32 on the bottom. So I have forced it to be 5 of something. 32 is 2 to the 5th. So I have 5, I need 5, those cancel out. I just am left with a 2. My top stays the same. So we get the same answer both directions. Okay, so let's look at our notes worksheet. Okay, if it's a monomial, we're simply just going to multiply the numerator and the denominator by the exact same thing. Okay, why would we do that? Let's look at this one. When this has the square root, or when you have any index here, square root of 5, I already have 1 5 here, so I just need 1 more. So when I multiply by the square root of 5, I now have 2. I have 1, 2, and I needed 2 of them. Okay. So I multiplied by the square root of 5 on the bottom, square root of 5 on the top. These two just give me 5. Now, I've gotten rid of the radical sign. The 2 has to stay, though. So the 2 stays there. Square root of 5 times square root of 5 ends up to be 5. Now on top, I have 3 times the square root of 5. These can be combined on the bottom to be 10. I hope you're seeing that we just have lots of little steps. And I get 3 square roots of 5 over 10 for that one. Okay. Now in this guy, who's the problem? 15 is 3 times 5. This is an unwritten 2. So he can't stay on the bottom. I can't take the square root of 15. So we're going to multiply by the number 1, 15 over 15, right? So now I have to, those guys come out. He's on the bottom, so he stays on the bottom when he comes out, right? This on the top, I've got the square root of 8 times 15. So I have 2 times 2 times 2 times 3 times 5. I have a pair that can come out. So now I end up with 2 square roots of 15 times 2 gives me 30. So 2 square roots of 30 over 15 is my reduced answer, or my simplified answer for number 10. Right? Now, there is a special rule. There's a special rule when we have a binomial in the denominator, okay? So I'm going to go back to our foiling when we had our complex numbers, when we had I. When we were doing 3 minus I and 3 plus I, when we were trying to get rid of those i's, or when we FOILed this out, we noticed that we had 9 minus 3i, plus 3i minus 3i, and then these guys ended up with minus I squared, which turned into a number again. But we did it this way because the insides always canceled. And so that is called a complex conjugate. Okay, so it's an interesting word that means everything exactly the same, but the sign is different. So the 4 would be the same, the square root of 2 would be the same, and since I had a plus, I now have a minus. Now, when we FOIL any value, so a minus b, a plus b. We will always end up, remember the difference of squares, this is the backwards version of it. So now we're pulling up something that we learned in chapter 5. Same rule applies, the same thing. You're not learning anything new. We're just pulling up a rule from chapter 5 when we were learning how to factor out difference of squares. So a times a gave me a squared. My outers give me plus ab. My inners give me minus ab. My last give me minus b squared. These insides always canceled. And we got a squared minus b squared on it, okay? So we're going to use this same rule and apply it to the denominators here so that we can rationalize these denominators out, okay? When we have a binomial and we want to get rid of our radical, we know we have to multiply by the same radical to get rid of it. Okay, so we're going to make this a binomial. Remember, this is attached with addition and subtraction, so we cannot separate these guys. You cannot, absolutely not, cannot go 4 on top, 4 on the bottom. Oh, I'm left with 1 over square root of 2. No, that is wrong. Okay, so when they are attached by multiplication, absolutely, you could do that. These are attached by addition and subtraction, so you cannot separate these guys. Okay, so what do we multiply by? We just learned in the last one that we just find the same one and we multiply by it to make it go away. So in this way, we have to multiply by the complex conjugate. So we're going to take the same binomial and we're going to change the sign of it, and then we're going to FOIL. Now, we have to multiply by the number 1. So whatever we do on the bottom, we've got to do the same thing to the top, right? So now, on the top, we're going to distribute. 4 times 4 is 16. 4 times negative 2 is negative 4 square roots of 2. Okay, simple distribution for that guy. Now what do we have on the bottom? We're going to FOIL. Our firsts give us 16. Our outers give us negative 4 square roots of 2. Our inners give us positive 4 square roots of 2, and they cancel, which is what we want because we don't want any radicals anymore. Okay, so we got rid of those. So then my lasts give me minus square root of 2 times the square root of 2. These can be combined under the same radical. Square root of 4, square root of 4 is 2, so I've got 16 minus 2. Remember, when we have 2 of them, we're just canceling that guy out. 16 minus 2 gives me 14. So my top stays 16 minus 4 square roots of 2 over 14. Okay? Now, we would like to just leave that. It's not as easy as that. Okay? So, same rules that we've had before, and sometimes this is why I do not multiply these out first. I go ahead and leave them, I just write it where it's combined, because now, is this fully simplified? And the answer is no. Because all of these coefficient numbers have a 2 in common. So I could rewrite the top if I factored out a 2 as 2 times 8 minus 2 square roots of 2. I just took a 2 out of the 16 and a 2 out of the 4. And then 14 is 2 times 7. So now these are attached by a multiplication. So I've got a 2 on the top, 2 on the bottom. They go away. I'm just going to erase them. Now I've got 8 minus 2 square roots of 2 over 7. That is fully simplified. Now, had we kept this guy out in the first place and done 4 times 4 minus the square root of 2, and then multiplied by our complex conjugate and got 14 on the bottom, right away we could have said, oh, this has a 2 and this has a 2, and I'm left with 2 and 7. And then distributed the already reduced coefficient in that case. Okay, so let's practice that again. I've got 6 minus the square roots of 5. So this has to stay together as a binomial. My complex conjugate is 6 plus the square roots of 5. I've got to multiply by the same on the top and the bottom. So we're going to leave this out. I'm going to have 2 times 6 plus the square roots of 5. And on the bottom, I'm just going to do the first and the last because we know the outer and inner, we've just forced them to go away. So the first is 36. I've got negative times positive, which is a negative. Square root of 5 times square root of 5 is simply 5. So this leaves me with 31 on the bottom, which doesn't cancel with anything, so I can go ahead and distribute out my 2 and get 12 plus 2 square roots of 5 over 31. Okay. Now the important thing that matters is it doesn't matter if the bases inside are the same. It only matters what our index is. And so for all of these that are square roots, we can just use the complex conjugate. Now, if we're looking for something that is more, a cube, a fourth, a fifth, we have to kind of use this step that we learned initially where we've got to find the right numbers of them. Okay, so this was going to be some of our practice for it. So our wrap up for today is that we know how to add, subtract, and multiply radicals. We know that for addition and subtraction, both the index in value and our radicand base value must be the same. For multiplication, only the index has to be the same. For division, the index has to be the same. It's just top and bottom. We've also learned what rationalizing the denominator means, and it means that we cannot leave a radical in the denominator. We've got to move it by multiplying by itself on both the top and the bottom and moving it up to the top. And we've learned how to rationalize a binomial denominator with a complex conjugate. So our homework for this week is the 6.3 practice, the 6.4 dividing radicals practice, and there are 2 pages to that one. So again, do all the blue, then choose a salsa level for that one. And then the review, and this combines all of them, and it will tell you in the big black banners exactly what you're supposed to be doing on those. So for operations with radicals here, addition, subtraction, pay attention if we are adding and subtracting. Pay attention if you are multiplying. On these, we're distributing, so we're using all of our PEMDAS rules. We've just added a radical to it. When we work them with rational exponents, always remember the base has to match, and then we use our exponent rules. So pull out your interactive notebook, pull out your exponent rules. Remember, when our bases match and we're multiplying, we add. If we've got a power to a power, sometimes it's easier to change it into its lowest base. So lots of different ways that we're practicing with rational exponents. This is important because these are on the ACT, and I've got some of those to pull up for you for that. And I think that is, so this review one is your last one for your homework, and then we've got a little quiz to just test your knowledge and see how we wrapped it for that week. So have a great week,